Today's speaker is Mykola Vovchanskii with the talk on here is different types, point densities in Arratia flows, heat potentials, and algebraic decomposition of the Carlin-Macrae determinant. Please.
Thank you. So essentially today I will be recording something I visited at I think 2 of the previous seminars I participated in for a number of reasons. Firstly, because it proved relevant for something I'm involved right now. Secondly, because when finishing the work I found some technical difficulties. I still didn't finish them, but I will talk how to finish them and what were the nature of such problems, essentially. So let's start with quickly recalling what the Arratia flow is, but it's a standard which just have systems of coalescing Brownian motions, possibly with drift. Characteristic feature is that they're independent before they meet and they merge afterward. I will use notation X for this notation, but if S is equal to 0, I will just drop the first subscript. The Arratia flow with drift is essentially the same system of coalescing, but are Brownian motions. But now we allow drift to influence every particle separately. So every particle will be written as a solution of this stochastic differential equation, and this WST is the noise that is specific, belongs to this very particle. I will also always assume that noise is at least Lipschitz continuous and bounded, though some results can be formulated just for bounded noise, some results can be formulated just for Lipschitz continuous noise.
Lipschitz shift, you mean? Not
Yeah,
noise.
yeah, I'm sorry. I'm sorry,
Okay.
yes, you are right. Okay. So we know, and we recently have a talk devoted to exactly such objects that point processes for Arratia flow can be the Arratia flow generates a point process, and such point process can be described using so-called point densities or correlation functions, which is a standard term for physicists. Let's quickly recall what is it. So a standard definition of a k-point density, p, k of t. I will sometimes drop this k if it's clear what the dimension is to lighten the notation. This is a function of k variable such that for non-negative or just for bounded without this assumption of negativity, the following holds. So we can calculate a function. Here we need to think that we essentially calculate all the points that have survived for any brow. Arratia flow, the corresponding point process is nowhere dense. We can take any function and we can recalculate such functionals in the left in the terms of the k-point density. I will need a modified definition too, which was introduced by Professor Drogovs in me during my PhD studies, that a k-point density that corresponds to a starting point x is a function that satisfies the very same essentially relation, but now we consider only particles that start from this specific x. So generally speaking, n should be at least equal or greater than k, but you can define any k-point density for k from 1 to n. And this indicator, I will always write indicator in this form. So 1 and a square, a set of square brackets, just guarantees that this makes sense. The existence of such objects quite directly follows from the so-called Girsanov theorem for the Arratia flow, and we will recall partially this result later in the talk. So before proceeding further, let us tell something about fundamental properties of such objects that are well known. So standard two references is a joint paper of these researchers, including Professor Zabronsky, who is present. The second is another paper from Professor Tribe and Professor Zabronsky, and there are a number of results there that classify what happens in the Arratia flow. And generally speaking, it is shown, it is known that the point process associated with the Arratia flow is a Pfaffian point process with a known kernel. That is, any k point density, 2k point density can be represented as a Pfaffian of some matrix, and that matrix consists of cells 2 by 2 with a known structure. And the structure is expressible in terms of standard Gaussian integral ERCF and derivatives, first and second derivative. And the Pfaffian is an object similar to determinant, so that this is just formal definition, we don't need it. In particular, one important application of the point density calculating joint factorial moments of the number of particles for the numbers of particles that hit a specific set. So by nt of A, I will always essentially denote the number of particles that that hit the set A at time t. And through in what follows, GT is always a standard Gaussian density, probably possibly multidimensional, and GT Km is just the Cardan-McGregor determinant, which is the density of the Brownian motion of the corresponding dimension killed upon leaving the first simplex. It is known that it is described by this determinant, and a very important set of properties of this function is given via these two estimates. This is a very powerful estimate in the sense that it cannot essentially be made any better, which is quite clear from the look of it. And it uses standard Mondor-Mondor determinants here and here. And it essentially provides an estimate from bound from below in terms of just one-dimensional Gaussian densities. Another interesting and strong result is this simple estimate. Now, I want to discuss a slightly different definition of endpoint density and discuss the proof of this result, in particular because we want to apply this, this proof to the case of non-trivial, non-zero drift, and give a proof that doesn't use some a priori estimates for the corresponding key point density. It can be avoided and can be worded differently, but this proof will show some ways to obtain estimates for key point densities in the case where drift is present. We will need additional machinery to be recalled for that, however. So I will always denote by B plus delta this one-sided ball surrounding A, one-dimensional ball always. And a standard definition of the alternative definition is that this is essentially this limit. So the number of particles that hit this ball up to times t, including, and divided by the joint size of these balls, assuming that these balls are disjoint. However, since delta goes to 0, this became small, the probability of 2 or more particles being here is small, and that means essentially one important result that you can just drop this n of t and just use the probability that all balls are non-empty. And the original proof, which we will rely on uses this trick. So the difference of these two can be estimated through this expression. And in some sense uses this estimate. I want to provide to discuss a different proof that uses slightly different machinery. So for that we need to recall something that has been discussed quite extensively on the seminars through the years, which is a coalescence scheme. So provided we have a finite set of coalescing processes without a possibility of triple collisions, so always only two can merge, a coalescence scheme is just a way to formally and uniquely describe the way these collisions happen. So we just enumerate all starting processes, say starting from below, and just write down the lowest number in the pair that suffered the first collision. Then we enumerate those processes anew and do the same, which leads to just, in this situation, 2, 1. We do not care about a specific time when collision happens, only the order. By ST of some coalescing system, I will denote the coalescence scheme at time on this interval for this process. In this case, this is particles in the Arratia flows are started at U. And this is just a way to write that there are no collisions. And then we can define a coalescence scheme that corresponds not only to some starting point X, but also to the situation when we observe exactly this coalescence scheme. So coalescence scheme guarantees that some number of collisions happen, in this case K, and that means that we can define point densities up to n minus K, of order up to n minus K. And the definition is exactly the same, we just here guarantees that there are exactly this many surviving particles. In contrast to the previous definition where we guaranteed that there are enough particles for this sum to make sense, we just here guarantees that we observe our scheme. Again, existence would follow, and for what we need, I need to recall some properties of stochastic exponentials for the Arratia flow, more precisely their finite dimensional versions. So firstly, we rely on the well-known standard fact that if you just have some Brownian motion started at U, and you just apply some merging procedure to transform this system into a coalescing system, for instance, allowing to survive the particle with the lowest number, if two particles meet, exactly as we did to write down a coalescence scheme, we can build a coalescing endpoint process, and this process will have the same distribution as the endpoint motion of the Arratia flow. Then we can define this object, the exponential, which is W of K. This is starting point. This is the case coordinate of this process at time t. So it's almost like the standard Girsano exponential, but instead of integrating from 0 to t, we only integrate to the times of survival for a corresponding particle. That means that if we have this situation in two-dimensional case, and this is where the particle died, we integrate not with respect to the whole trajectory, only with respect. So we integrate over the whole tree built by those, more precisely, a forest built by those particles. And then an application, what is called the Girsano theorem for the Arratia flow, states that this is the density of the distribution of the endpoint motion of the Arratia flow with respect to the distribution of the ordinary Brownian motion with no coalescence, just ordinary. So this is what we essentially want to prove. So instead of the number of particles, we only consider the case where it's not empty. I missed here product of indicators that there are non-empty. And the result I will use is as follows. So if you have this expression, so we observe a specific coalescence scheme S, and we have a product of this indicator and this exponential, and we take a conditional expectation, this conditional expectation may be rewritten as a function, which is defined in terms of Brownian bridges. So let us quickly call the Brownian bridge is essentially a Brownian motion conditioned to start somewhere and end somewhere. So Brownian bridge from 0 to 0 satisfies this SDE written here, which is well defined, but where beta k is some additional Brownian motion. And it essentially can be built from the original ordinary Brownian motion by doing this transformation. And then you can introduce very easily the Brownian bridge from U to Y by just taking the bridge from 0 to 0 and adding start and end in the proper sense. And then for every coalescence scheme, since we have this relation, and we know that we observe a coalescence scheme for the W U tilde, we can define proper set of meeting times in terms of this Brownian bridge. And we can write down an analog of the previous exponential, which is very similar, so it has a slightly different form, where we integrate not with respect to the Brownian motion, as in the case of the previous exponential, but with respect to the Brownian bridge, and we have some correction. And an important result about this function is that they are good, they are continuous, and then satisfy estimates of this type in L2 and many other senses. Now, if you want to return to the original problem, we want essentially to replace the product of numbers with just the product of indicators. Here we introduce the change of the measure, and here this is just a shortened notation that we observe exactly as. And using a telescopic type argument as usually, we can proceed as follows. We will do only the very first step. So we chip out exactly one number and replace this in the indicator in the right. And we use the trick we recalled previously. And the rest is just the same. And then we take a conditional expectation with respect to the values of the Brownian motion time t. Now, because everything is well measurable, we'll end with some function in terms of these exponents a, t small, which are well behaved, enough well behaved. And the rest just stays here. So we hide everything into this function f. And then the idea might be that we just look through all the possible values of our Brownian motion, forgetting that there was some coalescence scheme observed. So we knew previously that some particles would have died. We just forget about it and go through all the particles and just check where they hit in the corresponding set, where they contribute to this NG. For the first K, so this is just this part, and then we have something -1 here. And then, because we're doing this for a specific degree, we can get some estimate that take care of this n, essentially, and just replace the sum with the probability with the product that at least one is present here, because if no particle hits this set, this ng becomes 0. And at least 2 particles should hit the very last set for this to not be 0. And we have still this function, it's still here, so it survives till the very end. And in this very situation, we just then, because it's well behaved, we can take just the supremo over this subset, integrate over everything else that get here, without any previous estimate. What is important here is that if we were to use more detailed calculation, we would end with integrals of this function with respect to Gaussian density. So we essentially here we just out of n fix k first and forget about the rest coordinates. But generally speaking, this function is integrated with respect to them. And if you want to obtain some estimate through this method, you will get something like this. I'm not aware of good application of such estimate, but you can write. Now, extending this proof further and going further, we can define a representation of a J-point density that corresponds to some starting point and coalescence scheme observed in the terms of Gaussian densities. So for that, I of S, I will denote the set of coordinates that have survived. So we start with n coordinates, but possibly some of them died. And x to the power L just chooses those. And if I have something like I of SL, I firstly choose I of S, those who have survived. Then I choose a subset of J, exactly, because I consider the J-point density. Here and here, this is just minus because this is a density, a Gaussian density. And minus S means that I exclude those contained here. And essentially, the result is that you integrate with respect to those that do not survive. Your integrand is this function. And for J, you only control the behavior of J last. So you only know for this function what happens exactly of this subset. You go through all J subsets within all that have survived. K is defined by S. And essentially just leave out those that have survived included in this. This is the estimate in terms of Gaussian density. And the open question, for me at least, is to obtain something similar using the Karnin-McGregor determinant, because it feels more natural even. The problem is that you cannot do that easily, because you cannot easily work with the distribution of this object, a conditional distribution of this object with respect to this object. For this to make, to reformulate this proof into the direction I just mentioned, you need something to know something like this. This is hard, significantly. Now we can return to the previous system. For the result I want to discuss, I want to define another form of density that is obtained by considering only the Arratia flow restricted to the starting set of points. So the Enters law is just essentially uniform law here. And we will need another representation. So for that, I will need a recursive system of PDEs, which will mostly stay.
Excuse me, when you said entrance law is uniform distribution, what do you mean?
Yeah, it's badly worded. We just take uniform doesn't really make sense here. We just define the density, but instead of xt r in the definition, we consider xt01.
Okay.
Yeah, it's badly worded, indeed. And we will discuss systems of PDEs till the very end, essentially. So let us recall that if you have a very standard PDE, a parabolic PDE with Laplacian at the second order part, and some convection, essentially, inside of the simplex, you know that you start from 0. Sorry. You end at 0. I'm sorry. This is written, this is a backward equation. And you know what happens on the boundary. The solution is well known, but we will comment a bit on it to have a probabilistic representation. You just plug in the value of your process when it leaves and when it leaves, and it should make sense. It should leave. Should have left up to moment t. This is just a Brownian potion with drift A given here, and theta is the first moment it leaves the interior of the simplex. And it has this representation in the terms of this potential. So this is a standard surface measure generated by our Lebesgue measure in the space. And this is outward derivative. Or you can take, obviously, in almost any case, you can just take here plus and take inward derivative. It very rarely makes difference. And this is a fundamental solution. So if there are no drifts, it's just a current Mondego determinant. Now, for this to make sense, we need to add some assumption, obviously, on phi. A standard assumption would be the phi is bounded and Hölder continuous in both variables. However, generally speaking, you can allow discontinuity on the bottom of the parabolic boundary here. So f of 0, f at time 0 may not, at time t may not be 0. This is because Wiener process with drift never hits that pattern. But it's not a conclusion by the Feynman-Scott's formula, because Feynman-Scott formula requires a solution to exist. And now formally, this is, in our case, not a Lyapunov surface. It has angle. So, and typically, if it's not a Lyapunov surface, the problem arises. But here we can just take, for instance, f to leave only one hyperplane, or we can just understand that if we have equation in a half space, everything still works perfectly. And if you have this good equation in a simplex, nothing really changes, because you will be integrated, say, in some angle, and you will be taking, here you will take integral over points is the closest to here, and here you will integrate over points the closest to here. Essentially, we will be getting parts of the integrals that appear in the case when you have just half dimension, so everything is still well defined, though it requires some wording. And I will introduce the notations that the part of the boundary for the situation with xg and xj plus 1 are equal is just this, delta w and g. Then, provided that we have some coalescence scheme, then we can define m point density. M should be less than or equal to the number of the particles of the white. We have this expression. So we iterate these solutions, because essentially what this double layer potential gives you, it gives you the distribution of the heating time of the boundary, the distribution of the point, the joint distribution of the heating time at the point where it hits. And we essentially, again, do this trick by Probably not need here k. We go all through all the surviving particles and choose exactly m to use in this integral. And we just integrate. Essentially, this corresponds to the first collision, dt2 m du2 correspond to the second collision, and you have these expressions. And this is just removes something, in the sense that if we meet, then the two coordinates became the same. And this is not hard to understand why this exists. It's quite standard. Now let's return to the original question about the point densities for the Arratia flow restricted to start from the interval. So introduce u and g. This is j divided by n. And for such characteristic densities, we have the following results. So you can approximate them by using only a finite number of points, and the order of approximation is exactly 1 over n squared, essentially. This is what is written here. Uniformly in X. This doesn't. Well, it's not uniformly in X, it's locally uniformly in X. So un is just a way to write down this set with just 1 over n, 2 over n, 3, and so on. And I sometimes will treat this as a set consisting of this mesh. And I will introduce x epsilon, which x1 plus epsilon, x2 plus epsilon, and so on. So it increases the dimension 2 times. And this expression is equal to this limit. So this limit in terms of n, additional limit in terms of epsilon, a new parameter. And here we say that there are, for x minus a because it's a dual flow, and we need to switch this expression to the dual flow. And this is empty, so no collisions. And exactly one pair of points that start from xk and xk plus epsilon hit between the points of the initial partition. So exactly one pair. The rest, generally speaking, hit like this. So I will avoid recording all the theory of the dual flows because it's quite known. I just cite that formal proofs that dual flow for the Arratia flow with drift A is Arratia flow with drift minus A is due to Rabo, to the best of my knowledge. And it essentially says that we consider all the cases where this happens. So exists pair, in this case k equal to 2, that hits between. And the rest, the behavior of this doesn't matter as soon as there are no collisions. And this is essentially means that we know that there is a point from the whole flow that hits here. But if we start from this partition, these points of partition, they miss. And they miss in the terms of dual flow, they mean that they go around this. I do not know how to call it. So the set formed by these points in the dual flow. If we have easier simulation where our partitions are nested, this result is actually very easy to obtain. Let's quickly, I already presented this proof. I will quickly go through it one more time because at some point it fails, as I discovered. I will discover why it fails and how I'm going to repair it. So instead of considering just the difference, I will consider the results of integrating over half balls around xj, and then this is how this epsilon appears in the expression. There are m epsilons because we are dealing with the m point density. M is for number of points incident used to calculate the density, n is for step of the approximation. Now we know that we can get rid here from numbers of points that hit. We just consider a situation where they do not hit. They are present in this corresponding set. This is exactly that means that the full flow, I'm sorry, here it should be 0, 1, hits every half ball and one of these misses. It what follows for a moment, assume A is just 0, just Wiener process. And now I want to cite this result. So the Cullen-Malliavin determinant, if written in this form, so we separate this, we separate exponential, and we obtain a skew-symmetrical function. Skew-symmetrical means that if you take some permutation of coordinates, it will be the same with possibly a new sign. And since it's skew-symmetrical, a standard way for people proficient in this to divide it by the wanted determinant, obtain a symmetrical function, and decompose it in terms of the basis over in the space of symmetrical functions. And this base is delivered by so-called polynomials of Schur. And the result by the Chinese researchers is the following theorem, that this determinant can be written as the product of Montelmont determinants that are present, for instance, as a result of the Vovchanskii tribe and coauthors. And here stands an infinite sum. An infinite sum of some polynomials, I will explain in a moment, divided by this essentially a product of factorials. And this mu are collections of non-zero variables. L of mu is just the number of numbers here that are non-negative. And this mu essentially decompose explains how we can split L of mu, not L of mu, but the sum of all. L of mu, but the sum of mu, key, obviously. The sum of all into a rows of boxes. And then we can fill these boxes with letters from the alphabet 1n. And to make them unique, you need to expose the conditions that in this they cannot decrease, and this should increase strictly. And then this generates this diagram, and for every filling of this diagram with numbers from this alphabet, we obtain a simple polynomial. And the sum of all such polynomials is included in S mu of x. The proof is actually quite straightforward. It requires technique, but you decompose exponentials and then rearrange them using properties of determinants to obtain this. This decomposition is essentially the character decomposition in the terms of the corresponding permutation group. And it interests me because if you try to obtain some estimates for the Cullen-Malliavin determinant by hands, as it works in one-dimensional case, you will find that you cannot really group components enough. You cannot use conjugate class. You cannot do anything. But this is the way how people properly do it. Now, why it's important for us? This is important for us, and this is different in this strength, in this particular situation from the estimate obtained by the Vovchanskii tribe and co-authors, because it's not estimate, and thus we can use this to estimate the derivative. This is the difference. And Then we return to what we expected. We rewrite it in the terms of what we expect. So we split the sum into two sums. The first one is exactly one pair hits between points. The rest do not satisfy this condition. And the rest we put into one big probability that at least two pairs hit between. And if you want to consider the latter situation, you essentially need to consider all possible coalescence schemes. Obviously, there are a lot of them, but M is fixed. And then by the definition of coalescing of endpoint density, you consider the endpoint 2-point density because there are two, in the case if these intervals are disjoint. In the example, there is a disjoint. You start from 2n because x epsilon lives in R to n, and you consider two-dimensional density, 2-point density. But we know that it can be represented as a convolution of double layer potentials. And what is important, now we can plug in this expression for Carlin-McGregor determinants everywhere. And in particular, it will produce something that cancel epsilons and will produce even additional orders of n minus 2. Because this is already 1 over n, this is already 1 over n. But you can produce even smaller here, because there is Carlin-McGregor determinant, which uses y1, y2, and they're very close to each other. After the change of variables, obviously, this is after the change of variables. And it's very formal that how we push these epsilons, but it's totally rigorous because we push something from the integral which is not being integrated. So we allow to this, because generally speaking, when we work with such estimates, x divided by something, if you differentiate even the Gaussian density, you would get t to the power of 1 minus 2. And if you differentiate long enough, this will provide problems. So the whole bound is very good. If you want now, so we can get just rid of this. So what we need to do, we need to impose additional assumption that there are no collision happening. For that, you need to proceed slightly different. So we want also to obtain this condition. So we know that exactly one pair hits between. We know that only such collisions can happen, which is additional. Actually, it should be written everywhere here in all this situation, because it just guarantees this, those intervals are non-empty. But that means that in some pair, two particles are divergent in the sense that this goes up here and hits here, and this goes way below. And then we need not use the endpoint density, but we need to use the whole distribution of the processes, again given by some by this recursive sum essentially of double layer potentials. And we have like 3 points hitting essentially into small set, and everything works. Theoretically, one possible line of research here is to speak in terms of about estimates in terms of M. And this is an illustration that in one-dimensional case, everything is very good. You can just use a trivial trick, and you can obtain similar estimates without this knowledge of the algebraic expansion by hands, for instance, for 2-dimensional, even 4-dimensional Carlin-McGregor determinant, by carefully examining the sum. But it's tedious. I have done it. I was not aware of any way to generalize to higher dimension until I discovered that result. Now, the case for drift changes. If drift is present, everything failed because we do not have this representation. So my original idea was to get rid of drift by representing it as perturbation. So this is a generalization of the results that was obtained in one-dimensional setting in our joint paper with Professor Dragov. And I propose to do this as follows. So instead of using some probabilities, we will firstly switch to fundamental solutions with corresponding density. So let's introduce this operator. Again, for fixed M, we consider a fixed density. And we consider a very similar PDE with sufficiently good F. So I'm taking F to emulate that we want to obtain estimates at a fundamental solution. So we need to get something this essentially gets convoluted. If we treat this as a free term, by the Duhamel principle, we can just write down this expression formally. And iterating will lead to essentially the probability. This is not a probability to this term. And so substituting here this expression again will produce a series. And the k term in this series is given via this expression. So we are having good Carlin-Mondragon determinants, and all the drift does, it introduces these operators. In one-dimensional case, it's quite easy to prove that everything works. Before discussing what the problem is, let us look at two other different situations. So one can ask, what if we want just an estimate from above? So assume that we want to apply this method of separating drift to a probability that only a number of bad improper collisions can happen. Then we can just replace it with a probability that our drifted Brownian motion can live through some surfaces. Obviously, collision amounts to living through a number of surfaces in spaces of lower and lower dimension, but here we just think about the first value. Then we can write another PD, and we obtain another series. This series, so here we start with 0, and our boundary condition is just the indicator of those surfaces we're interested in. And this leads to another expression which is quite different to the previous one. The main difference is that instead of just differentiating a density, the Carlin-Mondragon determinant, we here differentiate the double layer potential. And while it can be shown in a standard way that this exists, actually obtaining the estimate that proves that this series is convergent is something that proved harder than I anticipated. And now the remark, you cannot push this derivative here. And generally speaking, when we think about properties of double layer potentials, one can cite the book of Vovchanskii, and I forgot the co-author, and paper of Oleinik and co-authors about the parametrics method and similar estimates. And also there is much newer results by Lucini, who proved a lot of results for double layer potential, but using very different method, mostly using Holder spaces and embedding theorems instead of direct calculations. But generally speaking, it's known that it's a good bounded function, generally speaking. This continuous derivative on the boundary. And that I said, essentially. So my attempt that I was concentrated in and didn't finish was to use the algebraic decomposition here instead of more standard calculations. And I will explain why it's proved harder than I thought. So probably a proper way to prove that everything is convergent is return to classical calculations. I want to also discuss the empty interval probabilities, which is very closely related to what were being told during the talk of Professor Zabronsky. So if we have some 2m-dimensional starting point, just point, we can define the corresponding intervals, and we can ask about the probability that half of those intervals are empty. This is an important functional because, firstly, it defines the point process. Secondly, the corresponding m point density can be obtained by differentiating this expression. So we differentiate in coordinates with odd numbers, and at the end we just took to each subsequent pair to be equal just to yk to obtain the result. And it satisfies this equation. And I was very interested in this partially because of the project I'm involved right now, and I will explain why. So firstly, here we have some conditions on at 0 and infinity. Generally speaking, all such equations, because they are set in an infinite region, should have some assumption by the behavior at infinity. But generally speaking, because we're interested only in those solutions that permit a probabilistic interpretation, something like just boundness typically is enough. Here we use the following boundary condition, that on the corresponding part of the boundary, it equals to the empty interval probability in a space of degree equal to the original degree minus 2. So we remove those points that met, and we use the values of the empty interval probability from the previous step to calculate the second, those on this new step. And another important moment that, generally speaking, here some starting distribution is present. It is exactly very related to what we were told in one of the recent seminars. And what is important here, that including the case of the Arratia flow, you don't need to know this whole hierarchy, this whole ladder, calculate. You don't need to calculate the whole ladder of such interval probabilities. You only need to calculate those that are expressible in the terms of a pair of motions. And that means that everything defined by how a pair of processes behaves. And a remark I want to make, that let us think a bit about what happens to some of these results if we consider a context of splitting. So we separate drift and pure Arratia flow with no drift. So let's recall, so splitting means that instead of considering XA, we replace it by introducing steps that consist of two substeps. On the first substep, we just run Brownian web, Arratia flow with no drift. Then we solve ordinary differential equation with this drift, so it's smooth. And then we use values here as an entrance for the next two to step, substep. And we repeat this. And then we either delete this part or this part, and in either case, you obtain some approximation of the original process. And if you think about some double layer potentials and those convolution of them, what is doable, you can use probabilistic formulation to prove the convergence of the corresponding expressions. You will need to show not only the convergence of times when particles meet, but the joint distribution of the particle and the place where they meet, but I think is doable. However, and this is one of the things that is on my mind, if you think about this interval, empty interval probabilities, they heavily rely on having boundary condition. And splitting in general doesn't react well to having boundary condition. In the sense that it's unclear how you fit the previous step into this next one. But let's talk. So why at least the part about proving the approximation result didn't happen? I considered this expression, and I was trying to obtain some estimate in terms of these objects. So recall, this is an infinite sum. So it consists of n parts, but those n parts can be of any length you want. And S mu is also a sum, a finite sum, but still a sum. Here, obviously, you have very good factorials, but still, the number, for instance, of diagrams satisfying this, it grows exponentially. It grows kind of controllable in some sense, but it still grows exponentially. And and on the other hand, we know that this is a well-defined function. But still, we know it's well-defined when divided by something like this. So by itself, it can grow quite easily. And I think that because you need to divide it, it's hard to control. There are a number of results, asymptotics of numbers of Schur polynomials, or alternatively diagrams for diagrams that fall into some subcategories you can split this infinite sum in. But overall, I do not know how to do this properly, so probably I should rewrite everything using more classical calculations. And that essentially leads to the plans of finishing work with series and some work related to splitting and whether the splitting can be used to prove that the Pfeffian structure of a point process generated by a coalescing flow can be preserved in the limit. And that's essentially all I wanted to tell today. Thank you very much for the attention.
Okay, thank you very much. Maybe someone have questions or comments, please.
Can I ask a question?
Obviously.
Thank you very much, Mykola. Very interesting. I am wondering, so this sum, this infinite sum you're working with, it is known how to write it as an integral over the unitary group.
Yes.
So this is this, yeah, it's the Baire formula, if you wish. And I'm wondering, would the integral representation be easier for analysis? Because after all, you have an integral over a compact manifold. The integrand is a bounded smooth function. So when you differentiate, you know how to do it.
I looked into it because this was the starting point in your paper. And
even though as you said, we didn't think about derivatives.
Yeah, I think I don't really see how to get a derivative estimate from it.
Mm. Oh, okay. Okay.
This is a problem because here formally derivation is very simple. You just
Sure. Yeah.
lose something.
Yeah. Right. So I was just hoping that essentially differentiating the integrand still leads to bounded functions on the complex manifold, so you can just use the sup norm to control the derivatives. But I could be wrong.
It didn't work to me, but it's been, I think, like 2 or 3 months when I tried this. Maybe I need to revisit it and look at and have another look at it.
Mm.
Thank you for reminding me about
Okay.
this.
Not at all. Thank you.
Thank
Okay. Other questions, comments, please?
I also have a quick question.
Mhm.
So do you have similar representations for multi-time densities?
For multi-time densities,
There are no simple Pfaffian formulas for those anymore.
you can possibly try to do it using Markov property. So let's do Markov property on the very first time. We know the distribution of the particles because such
Yes.
iterated such convolutions. Let me find it. They essentially give you, in some sense, the whole distribution of what is left of your flow. And then you would probably need to plug in simply into this starting endpoint density with a known starting point. So we'll have random density integrated with respect to this distribution. But it's quite just lengthy, not clear.
Okay, thanks.
I think that we discussed this things about multidimensional densities, and it looks like we need infinite series, like in Bogoliubov chain. Yeah.
Generally speaking, yes, this is. I think this is just a different formulation that hides it inside. Because
also,
yes.
it looks like still the idea with this coalition scheme and stochastic exponent can work. Actually, it works, for example, in the construction of Krylov-Veretinikov expansion for Arratia flow, initially in my paper in 2011. And I still am thinking that this stochastic exponent with coalescing will lead us to continual integral representation of point densities, even for initial Arratia flow and for Arratia flow with drift. So this is, I think, not a finished road.
Yes, it's interesting. Actually, yes.
Okay, and only one thing which I have to mention else is just a formal remark about the dual flow. It not only you have to say that it exists because it is defined as infimum of trajectories and so on, and it occurs that it is, and the noise we cannot choose arbitrary linear process. The noise is dictated by the noise of initial Arratia flow. Yeah. So it does not contain independent or so on. Wiener process. The noise is dictated
Dictate.
by the forward Arratia flow.
Yes.
But still, if we need only the consideration related to conclusions that we have empty interval or that, then of course we can forget about the relationship between this. Yeah.
Yeah, you can just think that you approximate the original flow with something smooth. You go to duals there, then you extract skeletons. They also would be convergent weakly, and then you reconstruct the flow.
In case of these flows, the dual flow can be constructed not only weakly. It is constructed
Yes, it is. Yes.
as a function.
Yes, the standard. So this
In
like
this case, the dual flow is a strong flow, actually, which is a functional of the flow.
Yes.
Exactly.
It's just not needed here at all. It doesn't matter in this specific setting.
Okay, so thank you again for interesting talk. And for today, that's all. Katerina, do you know who will be the next speaker for next week?
Yeah, the next week speaker is Nofer Salhi.
Okay, good. So for today, that's all. Bye and see you next week. Bye.
Thank you. Goodbye.
Thank you. Bye.
Goodbye.